Hello, and welcome back to my YouTube channel. In this video, I'm gonna talk about how we should prove the Heisenberg's uncertainty principle. So first of all, we gotta understand that unlike classical mechanics, in quantum mechanics, um, the standard deviation of the two position and momentum operators is given by this formula, which their product should be greater than h bar over 2. So I'm gonna just recap the operators in quantum mechanics. So the operator of position is simply given by x, and momentum's operator is simply given by h bar divided by I dx. So how should we prove the uncertainty principle? And I'm later going to explain what that means. So the general uncertainty principle is given by this formula, where the standard deviation or uncertainty of x and p is given by this formula. So the commutating operator of x and p. So this is the magnitude of these commutators, and we should commutate these two operators to get this result. So what does this mean? It's actually in quantum mechanics, if we operate x on p, this is not the same as operating p on the x. So the result is going to be different. So this result is not equal to 0, and we have to use some other methods to calculate this commutator. These are tricky to work with because they're Hermitian operators, and they differ a little bit from classical math and the classical mechanics. So what I'm gonna do, I'm gonna introduce a test function f, and I'm later gonna get rid of it in the end of the proof. So it's gonna be x pf minus pxf. This is gonna be x times pf minus p times xf. So this is gonna be df dx times h bar divided by I minus h bar divided by r I times, if we use the product rule, it's gonna be dx dxf plus df dx x. So this is going to be simply 1, because dx over dx is 1, and I can use the expansion to simplify this thing here more. So now I can cancel out these two operators here, these two terms here, and I'm gonna only be left with negative h bar divided by r if. So we can get rid of this test function f, and if we multiply both sides by the square root of -1, we're gonna get h bar I, and the magnitude of h bar I is simply h bar. So we found the commutator here to be simply h bar, and if we divide it by 2, it's going to be h bar over 2. So anyways, what does this mean? You might also see it written as in this form: delta x delta p is greater than or equal to h bar divided by 2. What does this mean? So imagine that I have a lake here, so there's a lake here, and it's filled with water, and I throw a stone here, and it creates a couple of ripples. So first thing that we gotta know is that in quantum mechanics, position and momentum is given by waves, and they're spread out in a specific distance, in a specific location. So if you look at this wave, the wave is not anywhere actually. Doesn't have a specific location like a box in quantum mechanics. In classical mechanics. In quantum mechanics, the presence of the particle is given by waves. So imagine if you drop a stone in the water and it creates some ripples. So the wave is not actually anywhere specifically, it's spread out over a region. So its position is spread out over a region. So now imagine that our wave is really confined to a small lake, and it creates lots of ripples when we drop a stone here. So we know the position wave very exactly here, but now there are lots of water waves overlapping here that makes the momentum and the strength of the waves very uncertain. And likely, if we have a very large lake, the uncertainty in these waves, the momentum of these waves, are have a very low uncertainty, but their presence is given and spread it out in a very large area. So this is what all the uncertainty principle is about. The more we know the particle's position, the more the less accurate we know the particle's momentum, and vice versa. And also be careful when you work with the Hermitian operators and you commute them, because if you do not use the test function like this, you might get an error. And actually this commutator here means that how much these two Hermitian operators of x and p differ, and how much uncertain they are. So anyways, this was the proof of the Heisenberg's uncertainty principle. This is the core idea in quantum mechanics. If you have any questions, please let me know in the comments. I'll be happy to answer your questions, and I'll see you next video.